Okay, thank you, Manuel. So, a very quick introduction of our institution. University of Pisa was founded in 1343, and with that is one of the oldest and most prestigious university in Europe. Our lab, research center Recuperaggio is a bit younger and was founded in 1965, and it targets two main research fields that are robotics and bioengineering. And the two of them collaborate and cooperate around four main topics that are mind, matter, motion, and manipulation. So these are some of the people working in the lab. We are quite a few. And these are the European funded projects that the robotic group is working on in the latest years. So with so many people and so many projects, we work on several different topics. I will discuss just the one that are more related to the natural intelligence projects. And I will start with adaptive and effectors. Here in Pisa, we developed this anthropomorphic hand, the Pisa IFT soft hand, that is composed of 19 degrees of freedom, but only 1 degree of actuation. And this confers to the hand a very low control complexity and also a very compliant and adaptable behavior, but also a stronger resilient one, as you can see in the bottom videos. Moving on, we also utilize the same idea of the soft hand to design a soft gripper that targets a slightly different topic, that is grasping objects with very different geometrical properties. This means very different size and weights, like fruit and vegetables, that at the same time are also very fragile. From that, we shift our focus from the hand to the foot, and we employ the same technology of the finger of the soft hand to design also the sole of a foot. And this enables to have a very adaptable behavior, so enables the foot to comply with uneven terrain and also to absorb shocks. And of course, we designed a version for quadrupeds. This version is also sensorized. That means that we can also reconstruct the curvature, the shape of the ground while working. And this will be used in the natural intelligence projects. I mean, a new version of it, of course. We also worked on actuation. We're still working on it. And we developed these actuators that are variable stiffness. They present some spring inside of the actuator that confer to the joint of the robot a certain degree of compliance, of flexibility, and it's basically mimic the functionalities of human muscles. So if you want to move the link, you can simply move the two motors in the same direction, while with a co-contraction, so moving the two motors in opposite direction, you can vary the stiffness of the joint of the robot. With this built-in blocks, so with these actuators and the soft hand, we realized several different robots, and we'll present just a few of them. For example, to handle heterogeneous objects, we designed the soft handler that is composed of a soft gripper and a compliant manipulator. And this enables to adapt the position of the effector of the robot to the position of the object. And also it allows to grasp very fragile objects. For example, here you can see the robot grasping some eggs. We also worked on humanoids. So together with IIT, we designed the Walkman that is still actuated with compliant joints, with elastic joint. And the main target, the main goal of Walkman is to help human operators in disaster scenarios. For this reason, we also employed and tested it in a real post-earthquake scenario, like the one in Amatrice in 2016. And here the tasks were building assessment, data collection, and also object retrieval. Here you can see the robot retrieving some object inside the damaged house, while the operator is still operating the robots outside of the house, so in a safe position, that is the pallet station. And yes, you can see the robot taking the object. Still working on teleoperation, we also developed alter ego, that is a humanoid torso mounted on two wheels. The main goal of alter ego is to perform safe human-robot interaction. And as you can see here in the bottom video, we have alter ego playing with some children. But at the same time, alter ego is also able to perform heavy tasks. And this is thanks to the actuation and also to the hand. So as you can see, the robot is composed of our variable stiffness actuators and of the soft hand. So per the stiffness, we can perform different tasks. Okay, with so many robots, we decided also to work on benchmarking them and assessing their performance. For example, we designed this benchmarking setup to test the resilience of the hand and of the grasp of the hand in presence of impacts. And we used also the same idea to benchmark the balancing performance of robot in presence of disturbances. For example, here you can see our robot, alter ego, that is resisting some impulsive and repetitive perturbations. Okay, so we did not work only on the mechanical design of robots. In natural intelligence terminology, we can say that we do not focus only on the body of the robot, but also on the mind, and this means on planning and control. Starting with control of variable stiffness actuators, we explored several different solutions. For example, we employed optimal control to maximize the peak performance of our actuator. Particularly here, you can see how we focused on maximizing the impact velocity on the end of our trajectory. And here the solution was to basically exploit the springs, the mechanical springs that are inside the actuators, to store energy and then release it when needed. We also tested different approaches like anticipatory control, and the reason behind that is that if you use high gain feedback control with flexible joint robot, you have the drawback of stiffening the robot. So basically, you should avoid it, and this is the reason why we tried also feed-forward approach, so anticipatory control. In particular, here, this controller is based on iterative learning control, and basically, the robot repeating the same task several times, it learns how to do it. So yes, in this video, you can see the robot learning how to perform the task. At the beginning, it is not able to pass the obstacles, but at the end, as you can see, it is able to track the desired trajectory. Okay, we work also on locomotion. For example, we target efficient locomotion with this planar pivot robot actuated with elastic actuation. And our approach here was to use numerical optimization to minimize the cost of transport. So we perform hundreds of simulations, and then we simplified this complexity through principal component analysis and primitives. And at the end, this is the result. We could use it online, and we could also vary the velocity and also the height of the step of the robot, and we could do it online without losing performance, so in an efficient way. As I said before, we developed this novel adaptive foot for quadrupeds, but this comes with the problem that most of the full-told selection planner consider only point or flat contact. For this reason, we designed this planner that is based on convolutional neural network, and basically through the shape of the ground, the curvature of the ground, and also the kinematics of the robot, the planner chooses the best spot where to place the foot. Okay, finally, if you want to move in a structured environment like the natural one, you have also to consider interactions, because they are usually unavoidable. So interaction can be desired or not desired, and a typical solution to this problem is the employment of impedance control. But impedance control comes with the problem of choosing the gains. So different tasks or different scenarios may require different impedance behavior. So to avoid that, we developed this planner that chooses the optimal gains to maximize the robustness of our system in presence of disturbances and yes, interactions. So for example, if you use fixed time impedance, like in an upper row, you have that the robot fails past the obstacles. That is unperceived, so the interaction is not desired. While if you use our controller, the robot is able to pass the obstacles without any damage. Finally, interaction can also be desired. For example, if you want to push a button, you want to keep the interaction stable. And so there are issues related to the stability of the interaction, the resilience of the robot and of the environment, and also there could be positioning errors. And we found that there are some theoretical bounds on the Cartesian stiffness of the vector of the robot that must be satisfied. And these boundaries depends on uncertainties, on the shape of the environment, and also on the interaction forces. So in this video, you can see how if the boundaries are satisfied, the robot can successfully push the button, so execute the task, while if the boundaries are not satisfied, the robot fails. And there is slippage over the button. Okay, to conclude, University of Pisa is the coordinator of the project and will contribute in more or less all the work packages. And these three are the ones that we lead. Thank you very much for your attention.